I'd like to start off with a big thank you to our students who participated in the course, and also the universities and companies who helped make this all possible this week. It's been a big effort, as it was last year, to put this on, and we really appreciate all the support that we've gotten from the community, the medical technology community here in Costa Rica, and in academia as well. The objective of the course, as was mentioned, is really to introduce engineers to the product development process in medical technology, and also to prepare them for careers in the medical technology industry. So this is a lot to cover in a very little time. We took these students, and they come from engineering backgrounds, through the beginning to the end of product development in just really 4 days, because today was mostly spent on presentations. On Monday, we looked at the diseases that they'd be working on. We had them do a lot of background research to understand the problems that they would be trying to solve. We had them do a market analysis on the potential financial opportunity that their product could have. On Tuesday, Dr. Wettergreen taught courses on concept generation, how to brainstorm, how to come up with innovative ideas, and then how to select them down to just a few, 1 or 2 ideas. Those 1 or 2 ideas then go into prototyping. As the students will tell you, we prototyped with Legos, we prototyped with Play-Doh, we prototyped with all sorts of low fidelity prototyping materials to be able to create and communicate our designs. Then on Thursday, well, I should mention at the end of Wednesday, we talked a lot about intellectual property, how to do patent searches, how to find competitive devices, and then how would we manufacture these products for a very low cost. Thursday was a little bit more of this kind of strategy discussion on R&D, what we would do to further develop our product. Also, we discussed about quality systems. We had the students do a failure mode analysis. And then we ended Thursday with a discussion about regulatory and clinical strategies. Today, this morning, we've been spending most of our time preparing our presentations, which we'll be giving this afternoon. And I think the students are excited, maybe a little nervous, but mostly excited to give these presentations, and I'm very confident that they're going to do a great job for you. Throughout this whole week, the students have been doing what we call project-based learning. They've been learning something through a lecture, and then they've been applying it to one of their own projects. These are the projects that you're going to hear a little bit about. Dr. Wettergreen is going to explain a little bit about how the presentations will be formatted and about the competition. So I'll turn it over to him.
Just a few bits of housekeeping before we turn it over to the students. Students are going to present for up to 15 minutes. The students will not have any questions asked by the audience during or after the presentation. There'll be a period, as Dr. Richardson mentioned, where you'll be able to ask the questions to the students directly. The judges that we have up here are going to be judging the students on the following. Students are going to and have been asked to describe the problem or the unmet clinical need along with the market size. They've also been asked to demonstrate the solution to their need and describe it. Students are also going to overview strategies to implement this need, including the areas of intellectual property, manufacturing, quality, clinical, and regulatory. We've also asked the students to present with enthusiasm for their project, and I hope you'll see that, and I think you'll be impressed.
Erica.
My name is Jose Fernando.
My name is Sofia Rose.
I'm Gabriel. I'm Jose Paulo.
And we are Erica. So this week we've been working with this device right here, which is a bag valve mask, or BVM. So this is used on patients that are having trouble breathing. So this can be due to acute lung injury, respiratory arrest, low respiratory rate, hypotension, or during surgical procedures. So to correctly use this device, the user should squeeze it 10 to 12 times per minute. And the volume of air that the patient needs is dependent on their weight. So, for example, an average person needs 800 milliliters of air 10 to 12 times per minute. Currently, the doctors usually just do this manually and don't really have a good system to tell if they're giving the right amount of air to the patients. So, if the patients are given too much air too quickly, they can have injury to the lungs, oxygen toxicity, or ventilator-associated pneumonia. So this week we were tasked with building a device that would decrease the risk of these complications occurring. So in looking at our market, we decided to focus in on paramedics or other users in an emergency vehicle. And in Costa Rica, there's approximately 2,000 ambulances that are used. We decided that the willingness to pay would be about $75 US. There are devices on the market that do regulate the flow rate and the frequency of the air in these devices, but these are really expensive and they're usually huge machines that need to be plugged into the wall, so they can't really be used in these emergency vehicles. So we decided that our device would be much lower cost, so they could be used in these ambulances. So with these numbers, we found our predicted financial opportunity to be about $45,000 US.
Well, like focusing in the problem statement, we decide that we will design a way to address the inconsistencies of the back valve mask used in the emergency situations that paramedics attend. So they have some inconsistencies in what the volume and frequency are. So we want to ensure the accurate volume and frequency of airflow that the back valve mask is given to the patient. Also, based on this and what my partner mentioned, we established some design criteria in which we focus in ventilation frequency that it has to be among 10 to 12 times per minute. In the volume that, as my partner said, is measured by the weight, so we wanted to be within 50 milliliters of the set volume be established for each person. And the accuracy of both of them, we want accurate ventilation frequency and accurate volume of airflow to be sure there are not any complications, and it has to be greater than 90%. So.
All right. Based on the prototype, based on the design criteria, we make a low fidelity prototype that is that I have right here. With this one, we are solving the problems that we were mentioned. Okay. This design is based on something that is going to hold the bag and push it in a certain frequency that is going to be set by these dashboards. These dashboards are going to have some limits if you want to see it. You can press it, okay? So these are the dashboards. Those will have some limits that you're going to set according to the weight or the weight and the size of the person. So according to that a characteristic, you choose what the amount of air you want to ventilate. Also, those dashboards are going to return to the original position in a certain time. So with that, we are solving the frequency and the air volume that the person have to receive. Also, we made a CAD design, that is right here, and for you to understand better the product, you will have handles for make sure that person is going to handle very well. Also, they have this shape because we discovered that if you push it this way, it's going to do nothing. So the bottom part is going to hold it and does not allow this to displace. And also, this other part is going to push like this. This is a video of the design that we made, explaining how it works, so you can see in a better way. These are the dashboards, the handles, the way it's going to move. So I think you can see it's functional. So we consider that it's a good idea. This is the detail of the dashboards that we are going to use. The limits are going to be set in this part, so the dashboard cannot go longer than what we set. So that's our CAD design. Also, we made an intellectual patent strategy, and we found some devices that are pretty similar to our device, but all of them are electromechanical devices, so you cannot use it in any in all places. So we have the airbag squeezing device, the temporary pricing ventilator, all those have a low or medium IP risk, so we have a great opportunity with our product. Why? Because our product is only mechanical, so it can be used in Talamanca, it can be used in Upala, where maybe you will not have electrical supply closer. So, and this one is an example. It must be placed on a table. It will have a tank, and it have a very complex electrical and electronic programming inside. So it's not affordable for every ambulance, for every clinic. So we think if we make a mechanical device, only mechanical, it would be better for the places that cannot have these characteristics as this equipment needs.
So once we identified our prototype, we went ahead and described our manufacturing process. So we did an estimate of the process needed in order to manufacture our product. We're considering a burden labor rate of $15 per hour. So for each of the steps, we either have a cost associated with the materials and the cost associated to the number of workers that we need to assemble our product. So for a final average total cost of $25.58. We also did a failure mode and effect analysis. For this, we identified 5 potential failure modes, and we assessed them and gave them a different risk index. So the first 4, they have a risk index greater than 6. This means that these potential failures are acceptable in our design, and the only one that we need to pay more attention is the 5th one, the friction at the joint. So for the first one, we have the inaccurate dashpot distance. This means that the dashpot do not displace the correct length that we are needing. For this, we consider that it's a high severity but a low probability because it's going to be determined in our design. Also, for the next one is not the device not gripping the back. So this also has a high severity because if it is not gripping the back, the BBM cannot actuate and function on the patient. But this one is also considered in our design. The next one is the material breaking. For this, we did a stress analysis, and you can see it here. This one, it's very important because this one determines if our structure is gonna break. So with the effort needed in order to manipulate our device, we can guarantee that it's not gonna break. The inaccurate dashboard timing, that's similar to the first one, but that's also considered in our design. So the friction at the different joints, this is very important because if the friction is not considered, our device will not function in the appropriate way. So for this, we did a mitigation plan that focuses on choosing the correct material and giving it a constant maintenance. This will change our risk index from 5 that's undesirable to a value of 10 that's more desirable for our product.
Regulatory and clinical strategy. The device was classified as an FDA Class 2 medical device. In order to produce the device, it has to go through a 510K approval to make it consistently equivalent to the device and terminate a mandatory ventilation attachment, which is also a Class 2 medical device. As this device is not a Class 3 medical device, the testing should not be that rigorous. So as a team, we thought that maybe doctors, nurses, paramedics, and other people that handle the device should perform ventilations into manicules that are used into medical research and measure in a very high stress situation to measure the correct volume of air and the right frequency when it's used. Well, as a conclusion, current use of BBM led to inaccuracies in airflow volume and frequency. The use of a dashpot system regulates those 2 variables, and the design provides easy attachment to the BBM in an emergency situation. And as a summary, this device will help paramedics, doctors, and all persons that use this to reduce inaccuracies in the airflow volume and the frequency when it's used.
We are Glenda, Luis, Cassandra, Alejandro, y Alexis.
Okay, so a little bit about our problem first, since it's not really a disease, but it's still related to the medical field. We looked at a problem they were having at the pathology lab at the Liberia Hospital, where they're generating from 100 to 150 kilograms of pathological waste, as well as 90 liters of various chemicals per week. And they don't really have the way that they really wanted to come up with the disposal process for this. Incineration right now is the only accepted in-house treatment without going through a lengthy regulatory process in order to deal with this waste. Large incinerators, which we deal with this, are very costly. They go upwards of $300,000. So that's a little bit out of their budget. And right now, they're using external waste treatment and transportation, which is also very costly. So in order to come up with a solution, we analyzed the market a little further and assumed the following. We looked at public hospitals and assumed at 25% market share. And with that in mind, we saw a market opportunity of around $180,000. Not only that, we also expect that we can eventually extend to the veterinary sector, as well as the academia, since they have research labs and medical schools which could use this device, as well as private pathology labs. From all this, we concluded and we summarized our need with the following problem statement: a way to address disposal of pathological waste in Costa Rican hospitals that reduces environmental impact.
So for this, we established a design criteria. The first is the device must have a capacity of 1 cubic meter. It should take less than 3 hours to complete all the process and burn all the tissue. It must reach temperatures between 800 and 1000 Celsius. The CO2 emissions should be less than 20 ppm per day. It must have a downtime of 6 hours per month. It must have 100% compliance with regulation. It must cost less than $60,000, and it should have a lifetime span of 10 years. This is the sketch of our device. The device has 4 compartments, 1 optical system because it uses solar energy, and 1 chamber. So the process of the device is, first, the user puts the waste in the storage chamber, then a main piston pushes all the waste into an incineration chamber, then the LED systems the LED system captures the solar energy to preheat the waste and use it as an incineration. Then the gas emission goes through a pipe to another compartment to finish the combustion, and so it only reduces CO2 and water. Then, the pistons pushes the ashes to the ash tray so the user can take it away and for proper disposal.
So we analyzed, we did an IP study, and we found these 5 patterns. The first of them has a high risk, since it is a device that has the same function as ours, to treat waste, pathological waste. However, ours has an important difference, and it's that it implements solar energy to reduce environmental impact. The rest of the patents are medium-low risk, and all of them actually has a very expiry. So with that said, our overall IP strategy has a medium risk, and we would apply for a patent because of the different features that we have implemented in a standard incinerator.
For our labor burden and material analysis, we consider the process steps of building the device, which are assembly of the container. They're basically building the chambers. The hydraulic system consists basically of pistons, the ones that we saw on the design.
The ignition and heating system is the optical system that you saw, but we have also think of a fuel-based engine just in case there's not enough solar energy, but it's only for emergencies. And this is an automatic system for basically to improve safety and reduce some emergency that can be like an accident. We came up with a total cost of $50,800, but this is an approximate amount since we don't have all the amount of materials that we need. So we said that in line of production, we can even reduce this amount and it can be cheaper. This cost right now is lower than the one in the design criteria, so we said this is a good amount.
Well, this is the FMEA. There are several potential failures that we have for this device. We have three that we consider that are less likely to happen, but we also have to make like a risk index and mitigation plans for those that are related to lack of energy, the containment leak, and piston failure can happen that we consider that are less likely. So we are going to focus to these two. The possibility to damage the lens, that is our principal part of this device. So if this happens, it's going to stop working. So it's like a principal problem. We decided that a mitigation plan would be a protective shell or thicker lens. This is because the device has really high temperatures inside its chambers, and it has chemical substance, chemical gases that can cause really a lot of damage. And also, the exceed permitted toxic emissions. Our goal for this device is that it's friendly to the environment. So if we are going to do that, we need that it's really controlled. So this is one of our highest risk in this device. We assume that an overload alarm and a filter are going to be a really good mitigation plan for this kind of problems. And with this mitigation plan, the risk index are in a level that we can consider acceptable. Also, the regulatory strategy. According to the FDA, our device is not considered a medical device because of its functions, but we decided to investigate in our national regulations, all related to waste management and waste treatment. Is in charge of the Ministry of Health in Costa Rica. The regulations about emission control and incineration process are from the Ministry of Environment and Energy, INAR. And in case that we have the opportunity to sell this device in the US, the EPA is the institute for the institute in charge of the incinerator regulations, the 40 CFR. For testing, we don't have to do clinical studies because of the kind of device that we have, but we have to do a lot of testing. We have to make sure that all the goals that we promised are going to be achieved. So we need to test time taken, temperature, emissions, and the automation. We are going to use some regulations on like the ASME test code for emission. That is one of the use that people use in the United States, and different for each of the characteristics of the device to make sure that our goals are going to be complete.
Pathological waste treatment. We also develop a device that meets regulation, that has a competitive cost, and the most important is that it reduces environmental impact. So we are Medchem, and thank you very much.
My name is Juan Diego Barbosa. I'm Lautaro Ramirez. It's Carlos Luis Hernandez. Felipe Gonzalez.
I'm Jeanette Nelson.
Okay, first, to introduce you a bit to the background of the disease we're treating. Many people in Liberia, Guanacaste are experiencing trouble lately with chronic kidney failure, mainly in the agricultural field because of the inadequate water consumption and overconsumption of alcohol and painkillers. And there are also some factors that affect, such as diabetes or hypertension. Yet, when this disease occurs, the only solution is a kidney transplant, but only 10% of the population are able to get a transplant. So, in the meantime, or another measure to treat this disease is dialysis. The thing is that lots of people have to walk long hours to get to the Liberia hospital to get their hemodialysis treatment. So one practical solution is what we call CAPD, or continuous ambulatory peritoneal dialysis, which can be made at home. It lasts about an hour per treatment. And it consists of a system regarding 2 fluid bags and a regulator. So this fluid bag contains a pure fluid with lots of salt that is inserted into the peritoneal cavity in order to absorb toxins in the body. So once it enters, it absorbs the toxins and then comes out as a waste bag. The thing with this CAPD is that some people in Liberia have very low incomes, and we're talking about $1 to $5 a day. So they need at least 1 meter of height between the fluid bag and the regulator, and at least half a meter between the waste bag and the regulator. So some of them had to hang up of the ceiling the upper fluid bag, but some people in Liberia don't even have like a ceiling to hang the upper fluid bag. So we worked in designing basically a stand or a home station so that they can hang both bags, including a fish scale to measure the weight of the waste bag, and considering a very, very low cost. So there are about 1,200 new patients with this problem per year, and considering they have a very low income, their willingness to pay is about $30. And if we take this into account and assume values of 30% of the population acquired our product, we have a predicted financial opportunity of $10,800 per year.
The problem is to design an affordable device to support peritoneal dialysis equipment in low-income communities. The cost must be less than $30. The device has to be adjustable, stable, and transportable. That means a maximum weight of 15 pounds, and it has to be safe. That means no sharp corners or not pinch points.
So we're going to show you our final design after brainstorming and prototyping. So Dr. Richardson. So as you can see, this is going to be our device. It has 4 main pieces: a base with a hollow, so the patient can use sand, soil, or another material, and can add some stability for the sand. So we have like a table with an additional amount, so that can minimize the risk of the table falling off. As you can see, this is the patient scale. So we use the patient scale for more affordable for the patient. There is a regulator. All these plates. So to sum up, our 4 main pieces are the base, the table, the patient scale, the playback. So that's that. Now, for the labor burden and material cost analysis, our overall cost of unit is $29.97 US. So we reached our goal. It's lower than $30 US.
So this is our IP analysis, taking into account our prototype design and our prototype design and our target disease. We researched and we found out that these are the patents with the most relevant because some of them share the same features that our prototype. As you can see in the picture, one of them is very similar to our prototype, sharing the same characteristics. Fortunately, this patent is expired. So as a conclusion, we can say that our project has a low IP risk due to the fact that it's a non-complicated piece of technology and that most patents are expired. This is our FMEA chart. So during our design process, we took into account certain risks, such as the table falling off during the dialysis treatment, the whole stand falling off during the treatment, or the stand from breaking. Our main problem is the table falling off during dialysis because we think it's going to be an inconvenience and is more likely to occur. The other problems, because they are above 9 in our risk index, are acceptable in accordance to our design. So our mitigation for the table falling during the treatment, it would be to add a greater support to the table clamp mechanism that it will hold the table and lower the occurrence rate. And also, every patient that undergoes peritoneal dialysis has to undergo a treatment so they can have the treatment at home. So we think that including that device during the treatment will be helpful for the patients. And with clear instructions used and for proper training, patients will, and all other risks are acceptable.
We decided to classify our device as a Class 1 medical device. What this means is it is specifically for peritoneal dialysis. It is used for a medical purpose, but it poses no great risk to the patient. If it breaks, it likely won't cause any lasting harm or injury. Because it is a Class 1 medical device, we do not need to go through certain FDA testings, including the 510K, like any of the other medical devices have to do. That being said, we still need to comply with good manufacturing process requirements. We need to make sure that it keeps up a good quality, that it meets all standards, that it's labeled appropriately, and that people know how to use it, which goes into the training that we mentioned before. Like I said, because it is a Class 1 medical device, it does not need clinical trials to proceed to market. We do want to make sure that it acts as it's required to, though. So we will be testing it before we give it to the customers. These tests will be for our customer requirements. We need to make sure that it is easily transportable, since sometimes these people need to move it long distances from the hospital where they're likely to get it to their homes. It needs to be stable, it needs to be adjustable, and it needs to be cleanable in case something happens. It also needs to be tested for efficacy, or usefulness, and safety. We need to make sure it performs as it's supposed to, and since many of these patients have large families, make sure it's safe for both the patient and the patient's family. We were given a task to create a stand for people who have peritoneal dialysis at home and currently, because of low incomes, can't afford the procedure as it is now. We had many customer requirements. It needed to be transportable, it needed to be safe, and it needed to be inexpensive. Our product, we believe, meets all of those requirements. We kept it low cost, and it performs as we want it to. We are glad to say that it meets all the requirements. Thank you very much.
My name is Michael, and I'm here with my teammates, Anna Maria, Elizabeth, Marlon, and Daniel, and together we make up Team Shot Through the Heart. We'll be discussing our device for the treatment of cardiac tamponade. So what is cardiac tamponade? It is a heart condition that affects the pericardium, which you can see here is the sac that surrounds the heart. It provides lubrication as well as protection for the heart from the rest of the body. A cardiac tamponade event is characterized by fluid buildup in the pericardial sac, as you can see here. When this occurs, there is increased pressure on the heart, which then leads to decreased heart function. It makes it harder for the heart to actually pump. Current treatment methods are mostly needle-based, so a needle goes through the chest to the pericardium and extracts the fluid. These procedures, although they are effective, are costly, require a lengthy procedure, and have no measurement or sensor on the depth of the needle. This proposes a huge risk of going too far into the pericardium and puncturing the heart. This condition affects around 2 out of every 10,000 Americans every year. The majority of those affected are adults between the ages of 20 and 50. So that is our targeted market group. Based on that group, our estimated market size is 36,000 people per year in the US. Based on or referencing current technologies and current procedures, we found that our customers' willingness to pay is around $470, and this includes the device cost as well as the surgical fees. Those two numbers multiplied together with our predicted market share of about 20% come out to a total predicted financial opportunity of $3.4 million per year.
Well, so we define our problem statement that, as you can see, is that we will design a minimally invasive device to remove excess fluid from pericardium, with the goal of reducing the procedure time cost and also total cost of this device. Our principal design criteria are based on, for example, the first one is that we must reduce the fluid of pericardium and to a range of 50 milliliters. Then it also must be easy of use because, for example, personnel like cardiac doctors must be able to be used. Also, this product take less, or for example, take an hour in all the procedure. Also, then we have that we study the penetration of how deep it goes. And finally, we propose that this product takes a cost, for example, around $470. Okay, so having those criteria in mind, we started brainstorming and we came up with tons of ideas. Right now, I'm just going to show you like our wildest one, and it starts with the spongy mesh. So we thought if we get a needle inside the body and inside the pericardial space, we could kind of insert some sponges so they could absorb the pericardial fluid. Our second thought was to use some kind of vacuum pump. So exactly as the first method, you just get a needle inside the body, inside the pericardial space, and with some kind of vacuum, you just drain the liquid. And lastly, we thought about using nanotechnology so we get those tiny robots or I don't know what else inside the pericardial space, and they will dissolve the fluid. However, through screening matrices, we just came to our final prototype that looks like this. It's just like the same with a handle, basically. It has a buzzer and it has deadlights for the alarm system. And well, this is basically how our prototype will look. It has a needle, and what we want to do is provide some kind of alarm of how deep you are inside the body so you won't actually touch the heart. So the needle is counting with some piezoelectric probe, so it will tell you how close you are to the heart. It also is going to be made of photoresistors right here. So we're basing our product on the principle that the deeper you get inside the body, the darker it's going to get. So based on that, we designed like an alarm system, a sound alarm system, and a light alarm system. So the doctor would have like an accurate knowledge of how deep he is. Here's the buzzer, and here are the lights. They work just like traffic lights, so when it's green, he's like free to go. When it's yellow, it's kind of like a warning that you should be more cautious. And when it's red, it means basically that you've got to stop. Right here, we have like a prototype of the alarm system. So this is the sound the doctor is gonna hear when the needle is outside the body. And as it goes deeper and it goes darker, it goes slower, so he knows he needs to stop.
For our intellectual property strategy, we decided to look for other devices that would handle the pericardium or have some sort of pericardium access mechanism. And from our investigation, we determined that such devices exist, as you can see in the images on the left. But most of these designs have something in common, that they try to extract the pericardium and then puncture it. And the way they do it is they have some sort of vacuum device that pulls off the pericardium and then penetrates it, so it's a little bit safer. Also, another example would be to have a device that clamps onto the pericardium, pulls it up, and then penetrates it. However, Also, through our brainstorm, we determined that such a process could be detrimental to the pericardium and could provide additional harm that is not accounted for. All right, for our LBM analysis, we decided to take note of what components we're using for the alarm system initially in the low fidelity prototype. With that, we can get an idea of how to build it on a larger scale with better components and better craftsmanship, so to speak. And after analyzing that, as well as the cost of assembling the alarm system, the syringe, and the needle, it will be around approximately $64.08. And the time to manufacture that would be around 1.62 hours, which translates to around 97 minutes.
So once we have like our idea design, like we selected our idea, we decided to run through a failure mode and an effects analysis to just kind of sort out the risks that it will involve and mitigate them as much as we can to have like the safest device possible. And what we found out was that there was actually a lot of very severe risk involved with our device. Like for example, the needle could break, or because it's made of all these materials, photoresistors, some of them could just peel off and then be left inside the body, and actually we would lose control of them, and so they could reach the heart or other organs and actually be very harmful for the patient. So the severity will be very high, but we're believing that if we design all the processes correctly and really control them all the way through, like you have good welding processes, you can make it so that the occurrence of those things is almost improbable. So when you put those two things together, you would get like that the risk indexes, as you see there, are high and therefore are in the acceptable range. Those are all in green. Now, that's not true for the last failure mode, which is an electrical shock to the heart. Since we're using electrical signals inside the body, and there's also liquids going in and out of the needle, we're thinking there could be a chance for just short circuits that we wouldn't take into account initially to surge inside of it. So that's very dangerous because you could basically give an electrical shock to the heart. So that's obviously not acceptable. So to fix that, what we will have to do is like go again through the design process and really focus on the electrical isolation and shielding, so that everything that's electrical is completely isolated and it never makes contact with liquids or with other parts. So what we would do is really design that well with high safety factors that allow us to raise that level to a level where we're certain that the probability of a shock occurring is actually improbable. So that would give us a risk index of 12, which would be acceptable. Now, as a medical device, we have to follow the FDA regulations. So first of all, they will classify us as a class 2 device just based on what the classification is to similar devices than the one we are designing. Now, we cannot file for an exception because we didn't find a substantially equivalent device, so there's nothing like to compare it with. Now, what we would like to conclude, and for all of you to get, is that we actually solved the problem. So as a bit of a recap, we were tasked with finding out a device that would help enhance the experience of the patient who goes through a pericardiocentesis. So one of the big things of the pericardiocentesis is the doctor has to know a way to stop once he reaches the pericardium, and then he has to stop before he reaches the heart. So by adding that alarm system that we're adding, we're giving the doctor more certainty of where he is, and so he can go faster before, and he will know exactly when to stop, and so reducing procedure time, which would in the end translate just to money, and so we would diminish the cost and enhance the safety of the patient. We do thank you very much for your attention.
Joaquin Rodriguez. My name is Ignacio Lopez.
My name is Ada Rivera.
I am Natalia Hernandez.
My name is Marco Murillo.
And all together we are Motion, Movement Solutions. Okay, so we have a problem, we have a need. And that need comes from this condition that is called arthrogryposis. So what is arthrogryposis? This is this congenital medical condition that has a a limitation of joint movement, as well as a low grip power. So I would invite you to imagine right now how hard can it be to get food from the table to your mouth without flexing your elbow with freedom or your wrist as well. Okay, it would be pretty hard, wouldn't it? You can't do this movement because your joints are kind of locked. So as you can see, this condition makes the patient to be highly dependent on others, and feeding is very complicated without any assistance.
Now that we know about the background of this aid, we can select our market section. In this case, we select the children from the United States that suffer from this aid from the ages from 5 to 12 years old. Also, we did some research and we found there are few competitors nowadays, and one of the most popular one is actually this one that is called Easy Hold. They sell a product that are bands of silicone that help these kind of people to grip their utensils for eating. Also, we found that the willing to pay of these clients are about $49 to $50. And by going to the CDC, that is the Center for Disease Control, we found that it is about 4 million newborns per year, and actually 1 per 3,000 suffer from this kind of aid. Using this data, we established a 26% market share, and we got 1,330 patients per year. And with the willing of payment, we got 70,000 US dollars per year as our predicted market opportunity. Also, we established our problem statement as the main goal to find a way to improve upper limb motion on children from 5 to 12 years old that suffer from arthrogryposis to enable them self-eating.
Well, our design criteria, our objectives are the following. Reduce the feeding time at least 40%, able to learn how to use the device in less than 7 days, weight less than 250 grams, and should maintain properties to from 0 to 120 Celsius, and should cost less than $50. Our constraints are must carry food, 10 or 15 milligrams, must be non-toxic, a material that is not going to be toxic, and must not have like a sharp edge, and this need to have our design. Well, our final design are the following. It contains 3 parts. It contains the bracelet, and contains the articulate tube, and contains the spoon. Well, this bracelet is going to facilitate the user to put it on and to take it off, and to make them to put it on by themselves. Also, it's going to have an articulate part that may fix in the place that is necessary for this kid. And it's going to have the spoon that it's going to have a form, a curve, that may help them to carry the necessary food to their self. So another part that is necessary to tell you is that it comes a part for exchangeable. It can be used by a spoon. It also can be a fork, or it can be a toothbrush. This because it needs to depend on the necessity that have the user in this case.
The intellectual property structure consists of main asserts of 5 patents of potential competitors. We found of this analysis that we have IP rates from all the patents from low to medium. For instance, the first patent is a spoon with a curve, and the last patent is about a bracelet and a stick and a spoon. comparing with our product, we can say they are very similar. However, our device have combined the bracelet and improved shape and curve of the spoon. Concerning the labor burning and materials LBA cost analysis, we, as was presented personally, our material, our product consists of 4 parts. We made the calculations for the process, the cost of the process of the materials, and we found the total average cost per unit was $12.15. Besides this, we also calculate the labor burning cost. We estimate at $1.26. So using these 2 values, we found the total cost per unit. It was $13.50. It's important to highlight here that our low labor cost was due to the fact that we are just going to assemble the parts.
I'm going to explain you the FMPA with our low fidelity prototype. As you can see, we developed a color symbology, being the green one, the acceptables, and the red, the not acceptable at all. So I'm going to emphasize with the not acceptable. As you can see, what would happen if the wrist is too tight? It can affect your blood pressure. Then it could get off very easily, and it wouldn't affect the user, but it would affect our design criteria, that is hold the foot. Then if a user is allergic to the material, it could affect its health, and then he could hurt himself. Then our mitigation plan consists in using a stretching material to control the risk adjustment and stronger alternative closed system to control the same thing. A cloth cover for those who are allergic to our product, and round edges for preventing themselves to poke themselves and hurt. As you can see, the end risk index is all acceptable. The clinical regulations, we define that our product wouldn't be a medical device. So it means that we are not going to make a medical trial, but we are concerned about our user. So we're going to adhere in some regulations and standards according to what I said before. And there are going to be regulations with the materials in contact with food and in contact with the skin, regulated by the FDA and European organizations.
Well, as a conclusion, through the development of this device, we look at the main or the principal need is the self-feeding for children from 5 to 12 years old with arthrogryposis, and we face it based on engineering design process, focus in our design criteria as a self-read, flexible, and other ones, and all those led us to design or final device in order to improve the movement or those sides and to reduce the time for self-feeding for the users.
Do you want to see your kid self-fitting? Then try our movement solution. You're testing in an easy way. Thank you.